Hi everyone. So for this lecture video, basically I would like to discuss about the supervised learning on chapter number 7, discussing on the Perceptron learning rules. So let's get started. So in this particular video, basically we will talk about the learning outcomes at first. So why we need to do this particular study, why we study this topic. And then we will talk about the Perceptron architecture. So we will jump to the single and multiple at the same time. And we will discuss on the rules which related to the perceptron itself in order to learn. So in this particular subtopic, we will have given input and output for a certain perceptron, but the idea is how we modify and learn the best weight and bias in this context of single neuron. Okay, so we will test them in particular example given later. And constructing the learning rules, basically we will talk about the error equal TA and things like that. So we have the, how to say, this one, the condition of that one. So one is the first category, second and third category, which we might stop the trainings after we reach up to the error 0 at this particular point. So we will do I will show you some exercises afterwards during the lesson session. Okay, so for the outcomes, basically the first one is to describe an algorithm for training perceptron networks in order to learn the classification problem. So here, the things that been focused on in this video is supervised learning, whereby the classification is our concern. So particularly if we have the boundary line, so that would be example, this is 1, this is 0, or in binary, or this one is A and B categories, or we can say that this one is cat or dog. Okay, so things like that. So then the second objective for this video is to develop the perceptron learning rules. So this one is the most important here. So basically, in order to do this, basically we need to find the weight and bias considering the 3 conditions. So EA with 1, with -1, and 0. So that would be the things, the purpose of this particular video, right? So to introduce this subtopic, basically one of the questions from previous section whereby we did cover about the classification before. How do we determine the weight and metrics and bias? So remember this one. So we have, this one is P1 and P2, for example. So this one is weight 1 and this one is weight 2, right? So this one is neuron. And this one is what we call it SN. So we have this one, by the way, activation function. So whereby it could be like the step function, or we call it hard limb, or we have sigmoid, and etc. Or we have Gaussian. Okay. So then afterwards we will call them as A output, or whereby this A is particularly depends on the N. Okay, in this section. So here the main priority for this class, this video, is basically to find, okay, don't forget to have bias here. So the main priority over here is basically to find this one and this one and this one. So based on the output given, okay, the input given, sorry for that. Okay, so then here we can have the discussion of if we have the input data is small amount, it can be calculated easily. So in this particular context, in the assessment or in the in the learning and teaching environment, basically we would consider this data input is small, so that we can calculate by our hands and so on. So, but when the network have many inputs data, it is impossible to visualize the decision boundary. So meanwhile, this is particularly for the programming Python and so on. Okay. Algorithm for training and perceptron networks will be described in this section. So we will discuss on how the network is learned to solve the classification, I mean the binary class. Okay. Right. So speaking of the learning rule, so how do the network or how do neutron, so this is neuron, learn by itself? This is a P, this is P1, this is P2, right? So this is, let's say this is N. We have X dimension, this is A, right? So how to modify the weight and bias of network so that we can produce the output as expected. So here, the layman or the main objective, layman terms, how do we describe it is how we decide this weight 1, this weight 2, and this in order to give the idea of when the given input in the future time, let's say we put it this data over here and this data. So this one is circle, this one is shaded or colored. So when we give this data like 1, 3, or this one is, let's say 5, 1. So the output of this particular A is equal to 1, and this A equal to 0 means we know that the A1 is belonging to one class, and the other way around, A equals 0 is belonging to another class. So that will be the motive of this learning, to find out how to learn these three things. Okay. So sometimes it also regards as the training algorithm. So yeah, there will be some resources saying that this will be known as the learning training algorithm. So type of learning rules, we have supervise and reinforce. So in this particular class, basically we will focus on this. Means supervised learning is the class has been given prior to training, right? Okay, speaking of the supervised learning, the learning rule is provided with a set of examples. So this will be the keyword provided. A set of example training set or proper network behavior. So it has an input and target. So that's the reason some thoughts call it as input output. So it is same, guys, input and target, okay? Because the things that related to here, so the input here is P1, P2, and the target is basically, so just now we put it N over here, so we have activation function. So target means, let's say P1 is 1, 2, so this particular P1 and P2, and the T when 1 is 0, for example. So given input, we have the target class for this given input is 0. So as I mentioned earlier, E equal T minus A, right? So the learning rule that we're going to have discussion afterwards is basically the differences between this target and the estimation, meaning the real and estimation become an error. So that would be A equal T minus A. Okay. So while oppositely in supervised learning, it is types of rule, the weight and bias are modified in response to the network input only. So that would be a different style. So they are not target out. There are no target output. This is the type when whereby it's suitable for the clustering operation with finite number classes. So whereby in this particular learning strategies, the the class is not been fixed prior to training, but it is happening and occurring simultaneous afterwards, we have the data clustering. Like this is the class A, this is class B. It depends on the data that we have at that moment. So without any teaching or learning. Okay, right. For this reinforced learning, it is similar to the supervised learning, but without correct output for each network input. It is provide grades. So this basically it reflects to the robotic departmental or subfield, right? Okay, now we will take a look at the what they call it, Perceptron architecture. So basically, the Perceptron architecture is built up to the network. So as I mentioned earlier, it's about the, remember this one I sketch it, and we have the bias. We have this, we have that. It's the same, guys. So this is EN. So this is N, this is P1, this is P2, and this is W1, this is W2. So it depends on how we portray the ideas, right? So in this part, so basically A is the output of the whole perceptron. Okay, so same as this one, whereby this W is weight, and the P is for the input, while B is for the bias. So that would be the similar of that. So this one is a bias, this one is the weight given, because obviously weight is multiplied with the input itself, and the N is output before we apply the activation function, the one that we discussed before. So we have several. Hard limit, we have sigmoid, and we have the Gaussian, bell shape, and so on. So in respective to this scenario, basically the way that the perceptron network has been presented as it is: A equal hard lim WP plus B, right? Okay, so in this particular perspective, development of the perceptron learning rule will be referred to the individual elements. Okay, so this would be the keyword. Individual elements meaning talking about the matrices. So because of W with P, right, and plus B, so this is the weight, and this is the either weight or input. Okay, right. So input is a matrix and W weight is a matrix, but the bias is not a matrix because the bias is standing alone. Okay, so that's the reason why if we have I elements of the row in W, so we can minimize this vector particularly by assuming all this one is I. Okay, so meaning it depends. So we pull all the thing to W I. Oh, sorry. Yes, sorry for that. This one to be here. Okay, so meaning one by one. Okay, right. So we define the vector composed by the element rows of on W is WI1, WI2, and so on. Okay. So perceptron architecture. So obviously weight is a matrix. I mean the vectors. Okay. So does the I element of the network output vectors become this? Okay, all right. So since we have the I in the hand, so because I is reflected to the T right now, so meanwhile every each of the I having the hard limb every each of the N, and we have this I, it depends on this. So we have this one here, right? It depends on the rows. So particularly, so BI is basically depends on the also the row has been chosen right here in element IH TH. Okay, so the B, because the B bias is basically happen when we have the numerical from the input, right? It depends on the matrices size. Okay, so this one is kind of revision, I guess. So hard limb is simple. So basically, if we have an output of a, oh sorry, because n is particularly need to be true to the activation function, right, over here. Okay, so say that, so this one 1, okay, this one is 0, right, n, so this one is a. Okay, so imagine that we have when a equals 0.1. Okay, so this one is n, right? So n is a, 0.1 means 1. So say that we have a equals 0.2 negative, meaning a minus e0 negative is 0, right? So there will be two output for this particular network. So this is reflecting to the class B or class A, vice versa. Okay, so yeah. And then each neuron in the network divides into input spaces in two regions. So I think we did discuss about this, two regions. So meaning this would be the shaded or to differentiate. So this one is 1 and this one is 2. So meaning the idea of 1 is here, the idea of 0 is there. Okay, so separating those field. Okay, so perceptron architecture. Okay, this slide shows that the we are discussing on the single neuron perceptron. So whereby this one, okay, right. So input given as P1 and P2. So we have two inputs. Don't forget to about it. So we have the weight. Weight is always coming afterwards the input. So bias is there. Okay, and whereby this is hard because the n is passing through the activation function as hard limb. So we have a equal hard limb bracket n, right? So the n is depending on the w and p. So that's the reason why we have here. So meaning to find a we have to find n. To find n we have to find w, p and b. So that's the thing. So in the whole story, basically a equal hard limb w, t, i, p plus t, b, sorry. So this one is depending on the ith input or rows, right? Okay, so hold on a second. Okay, so here we might say because of the wt here is written as kind of matrix, matrix, and this is vector. So whereby we can say that the I here is depend on here, and this T is particularly for the idea of pushing the matrix to become transform. Okay, pattern. Whereby if we have 2 0, meaning 2 0 this way. Okay, so 2 1 or 1 times 2. Sorry, this and that. Alright. So the decision boundary is determined by the input vector for which the net input n is 0. So okay, remember the one that we did discuss over just now. So this example, this is the boundary, this is 1, this is 0, right? So the line is basically reflected to here with the output is 0. Okay, with output 0. Oh sorry, this is minus 1. All right, happen if we discuss on the error later on. Okay, so to understand the boundary line, or we call it decision boundary, so all the element of w, t, p plus b is equal to 0. Okay, so now for example, let's assign the weight and bias as it is. So this is just example 1 1 1, right? So then the decision boundary is then, okay, so if we put this one, oh sorry, this to be 1, this to be 1, this to be 1, right? So meaning 1 times the P1, 1 times P2, the bias is minus 1, sorry. The bias is minus 1. So means P1 plus P2 minus 1 is 0. So P1 plus P2 equal 1. The same idea. So this is basically the line. Let's say we put it this way. This line, for example. So on the line, the other side. So the other side is 1. So the other side of that one is 0. So how to draw the line? Find the point of P1 and P2. So for example, we just put the any number to this particular P1 and P2 as here. So let's say that we put it P10, P21. Okay, P10 and P21 is 0, 1, right? So this one is 1, 0, right? So meaning this is 1, 0. This is 0, 1. So both of this point is basically on the line. So we can see that this obviously the boundary line. So this is just for example, right? Okay. So meaning for anything on that particular line is considered as on the boundary line, and the shaded area means A equal 1 and the other one is A equal 0. So it reflected to this N passing to the A N over here. So this is basically the one that we did discuss about right now. Okay. Okay, right. So we can conduct a test to determine which side of the decision boundary of 0 and 1. Okay. So now we just put any data. So it's not the any random data. For example, the data here is 2, 0 because of T. So basically the P right here is becoming to here because of the transform. Okay, so P is here and the weight over here is given as 1, 1. Remember this one, 1, 1, and the bias is minus 1. So this one is weight 1 and this one is weight 2 given. This one is bias, right? So we just put it here. 2 multiplied by 0 minus 1 equal 1. So this is 1. So meaning 2, 0 kan? So 2, 0 is basically here, the location of the data. So means the data is basically true for this category, shaded area. So that's the reason why A1. Okay. So that would be the idea of classification, the one that we discussed before. Alright. So we also can find decision boundary graphically. Okay, this is another way. Remember, this is the simulation to find the boundary in using graphically. So notice that the boundary is always, so read the sentence carefully. The boundary, decision boundary is always orthogonal to W. Okay, so what is W? So this is weight, guys. Okay, so this is weight. Remember, always orthogonal. So meaning the blue line is always orthogonal to the weight. So as illustrated here, so this is the weight. So this is the weight. So orthogonal means this line and obviously this line. Okay, so is the weight here, the what do you call it, the decision line is here. So then this boundary line is basically the WTP, guys. Okay, okay, so the weight vector W will always point towards the region where the neuron output is 1. So okay, this is the keywords in neuron perception. So the weight direction towards the arrow means the category is always shaded or 1. A equal 1. Okay, so that would be output is always 1. Right. So next is how to, so the problem over here is how to select the bias value. Okay, so bias value can compute by selecting the point on the boundary and satisfying the function. So whereby there are two things to be considered to select the bias is to find a point on the boundary. So meaning the bias is basically one of those points along this line. Okay, so one thing, and obviously satisfying the equation. So what is the equation of the boundary? Is this similar to this one? Okay, right. Okay, right. So here is the example for single neuron perceptron. Basically, we'll be discussing on the designing a perceptron network to implement a simple logic function whereby we have AND gate over here. So commonly, the things that will be given in this particular subtopic is input and target. So whereby the objective for this exercise is to find the weight and bias, guys. Okay, right. So commonly they will be giving this one is the input, this one is the target, this one is input, this one is the target, and so on and so forth. This one is input, this one is input, this one is target, this one is target. So meaning the data given here is supposedly to make this data to be a group of 0. Okay, so to be group of 0, to be group 0, this to be group of 1. Okay, so meaning this is the classification. So this data should be class 1, and the remaining 3 will be class 0. Okay, so in this idea, basically we portray them as a dark circle for the target number 1. So whereby this, because of 1 1, so the others is 0 0 is here, 0 1 is here, 1 0 is here, 1 1 is here. So this is the only one target for class number 1. Okay, E equal 1. Okay, right. So how we do it, basically the first step is select the decision boundary which separate the dark and the light circle. So how we're gonna do is basically to choose the line in order to separate two classes. So this side and this side. So meaning the line that has to be separated two categories of data. So obviously in the middle of this. Okay. All right. So then for this case, we choose the line to be halfly between two categories, right? Okay. So the weight is orthogonal to the boundary line. So just now we did discuss about the orthogonality of boundary and weight, right? So if we have this, so the weight happen to be here. Okay. So because orthogonal, right? So there are infinite possibly any length. Okay. So meaning this one, it could be here or here or here or there. So it depends on the how we choose them, right? Okay, so the first choice is basically choose this line just now to be as 2 2. So meaning the 2 2 is here and here, right? Okay, so that would be the weight. Okay, so finally we need to find the bias after we have because this is one example. So if we have the weight on our hand, so the second things need to be found by us is bias. Okay, so because we have the input and output, so we can pick it up a point on the decision boundary line and satisfying the equation. So the bias is basically any point in the boundary line. Okay, any. Right. So let's say the point of the point of P15. So this one is the data. So this one is here. So weight is there. So we have this, right? B. Okay. So example to find the bias itself, because the boundary line is making the equation to be 0, right? So meaning 3 plus b equals 0 because on the decision boundary line, okay, so we can see that b bias is minus 3 for that particular boundary line. Okay, so simple as that. Right, so we move to the multiple neuron perceptron over here. So the single neuron perceptron can classify into vectors into two categories, 0 and 1. So as we discussed earlier, right? So the multiple neuron, so this one is a multiple one, this one is single, can classify inputs into many categories, where each category is represented by the different output vectors. So it depends on the data given. Okay, since each of the elements output vectors can be either 0 and 1, there are total of 2s possible categories where s is number of neuron. So if we have one neuron, so meaning s equal 1 equal to 1. So s equal 2 equal to 2. So means 2 to 4. Okay. So categories in neuron, basically it depends on 2s. So that would be the correlation between this neuron and categories, possible categories to be found. Okay. Alright. So now this is the most important things to be discussed, perceptron learning rules. Okay, so the learning rules is basically the happen or implemented in supervised learning, which the learning provide a set of data. So for example, this one is input, this one is target. So 1 data, 2 data, 3 data, and n data in QA. So as each input is applied to the network, the network output is compared to the target. Okay, so this would the way it is when you give PQ, so the network supposed to find the class as TQ, suppose, but not really, because that what we call it error afterwards. Okay, so remember we have this one just now. Okay, so the learning rules then adjust the weight and bias. Okay, so during the time for having this data, and this data, so the learning rules will adjust the weight and bias for multiple time until they reach the weight and bias error become 0. So that would be the keyword over here, guys. Until we found that there is no more error in finding or following the learning rules to find weight, to find the error of the weight and bias become 0. So then we stop the learning process. Okay. So to see it in a clear picture of the implementation, so basically we will use the this example. So input target. So remember input target. So whereby input and output lah. So the target means it is clearly to say that the data is belonging to what class, either 0 and 1. Okay. So remember the dark is 1 class. So I think over here. So this one is class 1 and A equal 1. So this one is A equal 0. But for time around, because we still don't do that, so we don't call it as A, we call it as a T again. Okay. So because the T12 here is supposed to be 1, okay, in the data. So minus 12 is supposed to be 0, and 01 is supposed to be 02. That's the reason why we do it round circle without any shade, black shaded, right? Okay, so for this case we have 2 inputs and 1 output network. Okay, right. So letting the network free from bias. So what does it mean, free from bias, guys? Okay, this one is very nice, interesting. Okay, free from bias meaning B is 0. Okay, so it's as because of since we have input and target given, so we might find this and this, right? So but this is obviously 0, so the network is as it shown figure. So meaning we don't need the b equals 0 over here because nothing happened and changed for this statement. Okay, we don't have any b. So this we can imagine that the decision boundary must pass through the origin. So okay, so speaking of bias, bias means without bias means that this statement is true. The boundary must pass the origin. So this will be the keyword, guys. Okay, so the blue line requires to pass through the origin 0 0. Okay, so the number of boundary is infinity. Okay, as shown in below. So basically the line that happen to pass the origin is varies. Okay, so they could be this and that and many more, right? Okay, so to one more, we want to have the learning rules that will find a weight. Okay, so because we don't need to find the bias because it happened to pass the origin, right? Okay, so remember weight and bias. Okay, sorry, weight and the boundary line is always in orthogonal. Okay, so means if we have this as boundary, so this would be weight. So if we have this for the boundary, so this would be the weight. So always orthogonal. So mean this is weight. So this is the boundary line, okay, or decision boundary, right? So that would be common to all the things that happen in the classification by neural network. Okay, so I just copy this element as our references to be here. Okay, so that we don't need to jump in and out, go and there over there again. So how to test them? We need to construct the learning rules, guys. Okay, so the first step is to initialize the value of the network parameters, weight and bias. Okay, so now we need to initialize ourselves, okay, about the weight and bias. Since the bias is how to say, considered to be as a 0 at the moment. Okay, where is it stated, that one? Okay, here, free from bias. So we need to declare the weight. Okay, need to find the weight. Okay, so first there is no bias. Oh, okay, written here. So thus let's initiate the weight vector SWT. Okay, so all we need to do is basically to initiate, whereby this is basically the one that we want to give to the input given as this one. Okay, so we need to have a weight for this 1 2. So unless if we don't have, so the neuron is not working. Okay, so means this one is happen to be 1 0 and 0 0.8 negative. So we try to initiate this value. And okay, remember the hard limb is basically WT and P. So why it doesn't have the B? Because the free from bias. So we don't have this. Okay. So now the weight that we initiated is 1.0 minus 0.8. Okay, right. So the input given is 1.1 and 2. Okay, so we put here 1 2. So basically, the one that we have over here is 1 0 plus minus 1.6. So now we have minus 0.6, right? So this value is basically need to follow the activation function as hard limb 0.6. Okay, so remember this is 0. So this is N, this is A, right? So 0.6 meaning, let's say this is 1. So 0.6 is over here, guys. So means that when n is 0.6 minus, the a is 0. So that's what we have 0 in hand. Okay. So note that the 0 from the estimation, the value from estimation is 0. But the target is basically 1, guys. Okay, so it is giving us as an error. So later on we will discuss about that. So suppose the data should be 1, not 0. So that will be further discussion afterwards. Okay. So meaning here, okay, let's say here is 0, right? Okay. So the one that we picked just now is 1 minus 0.8, right? So the weight, remember? So we can see what happened by looking up to the following figure. So the initial weight vector result in decision boundary that incorrectly classified the P1. Okay. So remember the weight direction over here. Okay. Because this one is, remember, it could be any from passing the origin, right? So any line, it could be here, it could be here, it could be this. Oh, sorry. It's not passing through the origin, guys. Okay, it could be here, right? Oh, sorry, again. Oh, okay. Okay, so the one and this one is 1, and this one is 0.8. So this one is the weight, guys, the vector of this. Okay, so we need to alter the weight vector so that it point more towards P1. Okay, so where is P1, guys? This one. Okay, so this weight is particularly dedicated for this 1, 2. Okay, so we need to alter the weight vector so that it point more towards, so meaning towards the this point. So what we need to do is basically to try to alter this value for having a new value. Okay, so the way to do it is to, so the first is set W equal to P and P add to W. So in the neuron perceptron learning rules, basically the method 2 is chosen. We wanted the W weight vector to be updated, guys. Okay, we don't need to have the equal number for the weight and the input, but we need to update based on the given input. Okay, right. So to do this, basically the method 2 is repeated presentation of P1 would cause the direction of dW as asymptotically approach the direction of P. So meaning we need to make the direction of weight to be close to the P point. What point is this? This one, 1, 2. Okay, so then we need to use the sum. Okay, so this 1, 0 and 0.8 is considered as all right now, and all we need to do is want to find a new weight. So whereby the new weight is this plus the input that we have 1, 2. So we want to move this weight into a new location in order to get to the close. Okay, so the way it is, after we add this one, P is 1, 2, right? Okay, so P is 1, 2, and the original weight that we have is 1 minus 0, 8. So we add them. So 2, 1, 2 is basically, this one is 2, right? So this one is 1.2. So basically the weight is basically getting closer to the 0.1. Okay, so from here to here, right? Okay, now, so that would be good. That would be better for the first iteration, right? So next is to move on to the next input. So now we want to go to the next input, whereby the next input is now is minus 1, 2. So minus 1, where is minus 1, 2? Over here. Okay, so the next iteration, we wanted to find the weight for this. Okay, so in order to find the weight for this, basically we can use this one. So this is the new weight for the input number 1. So we we call the new weight and as the weight for the 1, 2. So that's the reason why we have this, guys. Okay, we do the hard limb and we found out that we have 1. Okay, so 1 is actually not the target of our data. So the target of the data is 0. So mean wrongly classified. Okay. So we need to update again the weight of the factor. So since, okay, we want the weight of factor away from the input. So we need to add because of the vector is too close. So we want to put them away from the input. So instead of addition, so we do subtraction. So remember, guys, this one we do addition, right? So now we do subtraction in other way to avoid weight to the from the point of input. Okay, so we subtract them. So current weight now minus the one that we have minus 1, 2 as the second input. So the second input is taken over here. So now we have 3 and 30 minus 08. So 30 minus 08 is here. Okay, so it's really too close, then we try to avoid them. So then we the new vectors is over here. Okay, right. Okay, now we know that we have two things done over here. So one is when the target is 1, we have 0. So then we have 1 over here, plus over here. When the target is 0 and A is 1, so we have minus over here. So that would be kind of things to be considered. So now we use this 3.0 and minus 0.8 to find the next one. Okay, so the next point is basically here, 0 minus 1. So we tried again, we have 1, but then we have 0 over here. So then it is contradict with our target. But again, we update the weight for that one with this data, right? Okay, so then we have this as a new weight. Okay, so this figure shows that the perceptron has finally learned to classify the 3 vectors. So meaning 1 vector, 2 vector, and 3 vectors. So we have this at the final one. Okay, for splitting all the way. Okay, all right. So then the third and the final is basically gaining the weight new and weight old is similar. So whereby the T finally is equal to A when we have this one. Okay, so when we build a hard limb again, so we find out that the A is 0. Okay, so meaning is equal. So meaning T is equal to A, right? Okay. For that matters, basically we found that we have 3 categories of the data. So when the target is 0, so the value of the estimation we have 1 or 0. So meaning we wanted to get close to them, we try to use plus. And this one, we try to avoid them, we use minus. And this one is whereby we have the equal, when we have T equal to, the estimation value is the same. So the weight is the same as a previous one. So that would be considered as our new weight. So that would be the process of updating again and again and again and again, right? So until we have that particular T equal A. Okay, so for this reason we could conclude that the test problem over here as to unify the learning rules. So there will be 3 rules in the previous slide that can be written as a single expression, whereby we have these 3 rules over here. So E minus 1 means, okay, so we take a look at the back here. Where is that? Okay, E is t minus a, right? So 1 minus 0 is 1. So that would be the first rule. And the other one is this one. E is t minus a is minus 1, right? So that would be second one. So we can conclude by having the three rules. Error equal 1 or error equal minus 1, there will be plus and minus. And this will be no error means equal. So that would be Simple's rule to be concluded over here, right? Okay, now, so looking at the first two, okay, I think that would be okay. Okay, so the absence of the third rules corresponded to the E equal to 0. So meaning there will be no error in the third iteration. So the three rules can be written by having this to be here is basically weight new equal weight all plus EP alias weight all plus T minus AP. So meaning this will be similar as this, right? So that would be the new rules to be done. Okay. So the rule can be extended also to be the bias itself. Okay. So this one is for the weight. This one is for the bias. Okay. So the B bias new is basically bias all plus the error happen to have after we calculate this one, guys. The AN. Okay. So then we have that one. And then from this particular point, from the above, the perceptron rules update the weight. Okay, update the weight vector of a single. Then the equation can be generalized by the multi. So this is might be followed by for the multiple neuron perceptron as well. Okay. So to update the row for the weight matrix are by adding this one, guys. Okay, EI. Because of we don't think of the multiple cases, so that would be things related to this. Okay, rows. So that would be IW new equal IW old plus EIP. Okay, right. So another perceptron rules over here is BI new equal BI old plus EI. So then in that notes, basically we can simplify all the rules for the learning rules for perceptron basically by having these rules. Okay, the capital W new equal capital W old plus error and PT. Okay, so this is the input by transform, and B new equal B old plus error. So that would be the things. Okay, so to get things in a clear picture, so we have one example over here. I guess you can take a look carefully over here. So given the test perceptron learning rules, okay, to test perceptron learning rule, consider again the apple. So this one is apple and orange recognition problem. So meaning class classification in the previous subchapter. Okay, somewhere. Okay, right. So this is the input given. So this is the target, guys. Okay. Orange and apple. So that would be if the input 1 minus 1 minus 1, it's supposed to be 0 as orange. Okay. So when input 1 1 minus 1, it's supposed to be 1 the input as apple. So that would be the case. Okay, so I put it here as a reference. Okay, so the first step is to as usual, the first step is initialize the weight and bias. So W and B vector. Okay, but somehow they put it this way and somehow they put it this way, the vector of both. Okay, so somehow they put it this way, the bool. Okay, typically we can initialize them with a small random number. Okay, so you can choose any number, small one. Okay, suppose that we start the initial weight matrix and bias. So this is the initiated weight matrix and bias. Alright, so we keep it there. So then in order to find the A for this first input, so basically WP plus B, right? So the A hard limb for this, okay, for this, so weight is chosen, so we just bring the weight over here. So the first weight, the first input is orange, okay, plus the bias taken from top here, so we count it, and 2.5 for the hard limb, basically 1 line, 2.5. Okay, so 1. So remember, the target is basically 0, guys. It's not same. Okay, so now we can calculate the error is E equal T A. So meaning T is 0, right? This one. So the A is estimation 1. So minus 1. So which one should we use? So back to this rule. So when we have minus 1, basically you need to use this one. Weight new equal weight old minus P, right? So what we gonna do over here is, okay, this one minus any. So the weight minus and input. Okay, so we have minus 0.5, 0 and 0.5. Okay, this is the new weight for after passing this one. Okay, alright. So while the B new bias, so B old is 0.5 plus error. Okay, so the error is basically taken from upstairs. This error, the same error, will be brought down. So we have the new bias is 0.5 minus. So this one is the new weight. So now we use this to the second input. Okay, so now this is second input. So we take the new here, 1 and 2 to be here. Okay, so now we calculate them, we have 0. So 0 and 1 is not similar, guys. So then we subtract them is 1. 1 means WT new W old plus, right? So the plus sign will be taken. So this one. Okay. So W old plus error 1 PT. Okay, PT is this one. So PT is just bring down there plus, so we have the new weight after passing through here, right? So the bias for this particular case is 0.5. Okay. So then I do it again by abstracting the first orange, but this time around we use this new updated weight and bias, okay, over here. So again we have 1. So 1 still we have error, so we do it again because 1 0 minus 1, so because of the supposed to be 0, right, over here 0 minus 1 is minus 1, so minus 1 is this, right? So we have a new weight, and obviously we need a new bias for the third iteration. So then we go again until we have also the fourth iteration. We again also use this one with the new weight and new bias until we have the error become 0, guys. Okay, so now that iteration would be stopped. So meaning orange apple, orange apple. So 1 time, 2 time, 3 time, 4 times. So this one is 4th time apple, okay. So we have error in the weight, okay. So that means that the weight is correct and bias is correct for the input P2, right? So then we try to check again if we use this one. Okay, we use this and this for any input. So now we have the hard limb as 0. So meaning this particular data is supposedly to be classified as 0. So meaning 0 minus 0 is 0. So that would be no error lah. Okay. So if we pick it up the first input vector, so it's not meant to be minus 1 anymore, kan? Okay. So yang ni 0 ni adalah this one, guys, equal to this. So that would be okay. Okay, so we conclude over here that perceptron learning rules is guaranteed to coverage a solution in a finite number of steps. So as long as the solution exists, and recall the perceptron learning boundary between the region is defined. Okay, so the boundary is basically this, equal to 0, and the things that have been discussed over here is linearly separable. Okay, so this is the solution, the exercise that's suggested to be done, and I think you guys can do the exercise 3 too for your improvement in understanding the neuron perceptron learning rules. Okay, I think that's all for this particular chapter. Thank you and bye. Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.